Bro, 6 hours of studying and you got a 53? It's over, Jack. Your ass is dropped. What's going on, guys? And in today's episode, I have a mustache. It's only been 13 days since I've shaved. Help. We're going to cover the 9 best features of Numpy featuring me, Maximus Alpha. Let's go! Although this video isn't about pandas or matplotlib, I'll use them to showcase some of the examples in the video, so feel free to import them if you want to follow along. So number 1 is Linspace. It gives you an evenly spaced range defined by the starting number, ending number, and number of elements. By default, there will be 50 elements. So if you wanted an array of 11 elements from 1 up to and including 10, you could write this. Now let's check this out in the console. And you can see we have our elements from 1 to 10 and they're evenly spaced by 1. So if the array is sufficiently sized, it will include the beginning and the end of the range. However, if it's too small, you could get something like this. We are looking for 0 elements, so it returned an array with 0 elements. Next, we only want 1 element, and since it begins from our starting range, it will only include that value. So we have an array with 1 element, and it is our starting range of 1. Kind of the same idea with 2 elements, except now it will return our starting and ending range. And then anything beyond 2 elements will generate those evenly spaced values. This is super useful if you need to plot something quickly and you want an evenly spaced set of values for your dependent variable. So let's try this with a sine curve and we'll graph it using Linspace. So here we're calling np.sine, and then we're going to be passing in a linspace from 0 to 10 with 2500 values. And you can see this is able to output our graph, and it's a very smooth curve because we have 2500 data points that was easily generated using Linspace. Up next is generating random numbers. So this is pretty straightforward, but you can have some flexibility with this. Maybe you want to generate a random number from the normal distribution, or possibly generate 5 random numbers of shape 1 from the gamma distribution. Or most likely just generate an array of random integers. So let's make an array of 100,000 random integers between 1 and 25,000. So now we can run all of these. Here's our random value from the normal distribution. Here's the random value from the gamma distribution. And here are our 100,000 random integers. And just to check, we can see what the size of this is. And we can see it is 100,000. Number 3 is Polyfit. Now, Polyfit can be used to easily create a polynomial of any degree you choose, and this function will do this by minimizing the squared error. So this is a CSV that I was able to get online. It has some made-up data between number of hours studied and these hypothetical scores that these children got on their exams. So let's see what this looks like if we graph it. Here I'm just graphing the hours studied on the x-axis and the grades on the y-axis, and this asterisk means I'm going to represent each data point as an asterisk on the graph. So this kind of looks like a linear relationship. In reality, it doesn't. It follows more of a sigmoid function, which looks like a flattened S. So if you were to follow my mouse, it would kind of look like this. Because you can't have a score below 0 unless your professor sucks. Or you can't have one above 100 if your professor also sucks. And a linear function has no boundaries, but let's use Numpy to easily make a 1-degree polynomial just to show you the power of Polyfit. So here I'm trying to create a polynomial of degree 1 between hours studied and the grade received. So if we run this, we have 2 values. This is the value of the coefficient for the first term, and this is the y-intercept. So now if we include a graph of our linear fit on top of our data points, this is what it'll look like. So the blue asterisks are the data points, and the red line is the line of best fit that we were able to create. And remember, we're looking at this from a 1-degree polynomial, which is why we have a straight line. But it shows you how quickly you can use Numpy to find relationships amongst data and easily plot it to be able to visualize that in a very easy manner. Number 4 is Polyvale. This is a good segue from Polyfit, as Polyvale allows us to evaluate a polynomial at any given value. So let's use the same polynomial that we made earlier and see what our model outputs if we were to study for 7 hours. Well, the results are terrible at 67%, which is horrible for 7 hours of studying. But what if we bumped it up by 2 more hours? Very nice, 95%, can't complain. However, this is why you can't really use a linear model for this. If I were to study 14 hours instead of 7, I get 167%. This is the class for me. Number 5, shuffling numbers. So this is really simple, but I like that it's so easy to do within Numpy. It takes your data structure and shuffles everything in place, so make sure that you know what you're applying it against, because the object will change permanently after you apply this. So here we have 100 evenly spaced numbers from 1 to 100, and we're going to shuffle it. So we start off with our first array, which is 1 to 100 in this order. However, you can see once we called random.shuffle and we printed b out again, it only returned b as a shuffled array, so this original array is now gone. Number 6, all close. So let's say we have these two arrays. All close is extremely useful if you want to check if two arrays are similar to each other rather than being equal to each other. You can check how similar the arrays are by modifying the tolerance. So the tolerance in all close will follow this equation, where atol is absolute tolerance and rtol is relative tolerance. Absolute tolerance is like it sounds, the values in the array compared element by element must have an absolute difference less than or equal to the tolerance you set. So if I were to set an absolute tolerance of 0.01, let's run this to see if all close will return a true or false. So we get true, and why is that? Well, each of these elements are within 0.01 of each other. It doesn't matter about direction, whether one is 0.01 greater or 0.01 smaller. It's just that they have an absolute difference of 0.01, which is specified by this tolerance right here. You can also measure relative tolerance, which multiplies the element in the second array by whatever parameter you set. So if we set a relative tolerance of 0.1, we'll get true. Well, why is that? Because it's multiplying 0.1 by each element in array 2, then looking at the absolute difference between the elements in the arrays. So let's walk through this. We can take the first value in array 2, 0.93, multiply it by our tolerance 0.1, and it's equal to 0.093. But now let's look at the difference between 0.92 and 0.93. 0.01 is indeed less than 0.09, so all of these operations were applied to each element, all of which returned a true statement. That's why when we set a relative tolerance of 0.1 for these arrays, it returns true. Number 7 is np_where. So np_where returns the index of elements in an array that matches a particular condition. So let's create an array with any number between 1 and 1,000, and it's 100 elements long. And let's say we want to filter this to include any element that is less than 300. So let's execute both of these in the console. So we have our test array and our filter. And this is an array with all of the indices where the elements are less than 300. If we wanted to then view the elements that satisfy this condition, we just have to apply this filter into our test array. Because this filter has more than one element, you have to use double brackets if you want to view multiple items by index in a NumPy array. If you only wanted to check one index, you would use single brackets. So now if we apply this filter, we can see that every item in this array is indeed less than 300. Number 8, transposing arrays. So let's say we have this array. Now let's run this and check the array's shape. So we have 2 rows and 8 columns. However, if we wanted to transform this into an array that had 8 rows and 2 columns, we can write the following. So now we have the dimensions that we want, an 8x2 array, but note that when you use transpose, this returns a copy of the test array. It does not change it in place. This is extremely useful for any sort of matrix manipulation and linear algebra, or really anything that involves modifying arrays. Writing the code to do this in pure Python would be clunky and inefficient compared to the Numpy packages, which have already been optimized. And number 9 is flattening arrays. Flattening allows you to transform a multidimensional array into an array with only one dimension. So let's look at test array once again. This is a 2x8 matrix, and if we wanted to flatten this into one dimension, we can simply write testarray.flatten, and now we have a 1x16 matrix, which we can confirm by checking the shape once again. So it's confirmed this is one dimension with 16 elements. So why would you use flatten? Well, if you needed to perform any kind of mapping, this can be a really easy way to apply this to every element at once, and then reshape the array based on whatever values are remaining. So I totally forgot to record an outro last night as I was entirely focused on shaving that damn caterpillar off my lip, but make sure to like the video and subscribe, and I'll see you in the next one. Your ass is dropped.